All right, in this video, we're going to look at a pretty special case. Roll that intro.
Do you feel the vibes?
If you hadn't picked up on it already, our special case is going to be called freefall. Freefall is when an object is moving through the y direction, and the only thing acting on it is gravity. Gravity provides a constant acceleration, which means we can use our kinematic equations. So the acceleration due to gravity, a sub g, is equal to 9.8 meters per second squared down. This means that in the y direction, this could be negative if we define our up as positive. We'll often shorten this a sub g with simply just g. So g equals 9.8 meters per second squared down. This may seem somewhat counterintuitive that a sub g, or g, is just equal to a flat number, because when we have an object that's heavier, we assume that it would accelerate more. But we're actually wrong. It doesn't depend on the mass or the weight of the object how fast it accelerates. All objects under the acceleration due to gravity accelerate at the same rate, 9.8 meters per second squared, in the downward direction. You can even test this at home if you'd like. Just try to pick objects that aren't breakable, but pick one that's heavier and one that's lighter, and drop them both at the same time. You'll notice that they also hit the ground at the same time. Now, maybe they don't, because you'll pick something like a feather. That's because of air resistance. In this case of free fall, we are assuming negligible air resistance, which means we aren't going to consider air resistance. So that might be another contributing factor to your assumption that a heavier object would fall faster and a lighter object would fall slower, is because a lighter object tends to be more spread out and therefore increases the air resistance. But if we can get rid of that air resistance, then they would all fall at the same rate. So now let's say you are the king of an area and you are overlooking a stampede of wildebeests to which your son is stuck. And you're there with your brother, and you slip a little bit while saving your son, and your brother decides to say,
Live the king.
And now you're in free fall. So this begs a question. You free fall 20 meters. Could you survive the fall? Well, if we look at the size of the cliff, let's say this is our cliff here. We could say this is 20 meters. You are starting up here, and you're going to fall these 20 meters. Well, we can figure out how long it takes you to fall 20 meters. So we could use our kinematic equation. In this case, we do a y final equals y initial plus v naught y t plus 1/2 g minus g t squared. If I consider up to be positive and down to be negative, that means that my g would be negative. It also means my y final would be 0, and my y initial would be the 20 meters up that I started. Since I was just holding on and my brother shoved me off the cliff, not pushing down, this would be 0 because my v initial y would be 0. So we would end up with 0 equals 20 minus 1/2 times 9.8 t squared. And it's at this point that we can solve for t, because it's our only unknown variable. So we would get 20 equals 4.9 t squared. So t is equal to the square root of 20 divided by 4.9. If we plug this into a calculator, we'll see that this gives us about 2.02 seconds. So this is how we can use freefall to figure out some information about stuff that happens, I don't know, if you're a Lion King. So if your question is less about the time and more about the survivability of the fall, we we'd have to try and look at what velocity you're going to hit the ground at. So for this case, you would have to use a different kinematic equation. V final is equal to V initial plus AT. And in this case, our V final is what we are looking for. Our V initial is 0 because we weren't shoved downward. Our A is going to be minus G, or minus 9.8 meters per second squared. And our T, well, we solved for T here. So our T is going to be this 2.02 seconds. That means that VF is equal to 0 plus negative 9.8 times 2.02. This gives about 19.796 meters per second. And if you think that that's not super fast, you are wrong, because that's about 45 miles an hour. So imagine hitting a tree going 45 miles an hour without your car around you to protect you. I would imagine the 20-meter fall would probably kill Mufasa, let's say. All right, guys, so this wraps up our 1D kinematics section of our kinematics series. Free fall as a special case is really important, and it'll come up quite a lot, especially as we move into two-dimensional kinematics and we deal with projectile motion. So, don't forget to hit like, comment, subscribe, all that shenanigans. I appreciate you.